Hello there, my name is Mahir Shahjalal, and I'm going to help you through hybridization and VSEPR diagram of xenon tetrabromide. The first thing we should do is make a Lewis dot diagram, which will give us all the information of bonds, electron groups, and geometry which are integral to the VSEPR diagram. And right now, I'm going to make xenon the central atom since there are more bromides than xenons. Now I'll make the bonds for the molecule, but this molecule follows the first non-octet rule, which states that any central atom that is a noble gas or halogen will only have sigma bond. We should still find the amount of electrons within the molecule, so we could figure out the amount of lone pairs that could be on the central atom. So we would bring out the periodic table and we'd look at where xenon and bromine would be all at specifically. So as you can see, they're both at 17, group 8, 17 and 18 respectively. And so that would mean that xenon would have valence electrons of 8 while bromine would have valence electrons of 7. We would then put this in equation to find the total amount of electrons. And so we would put 8 for xenon, as there's one xenon, and there would be 7 for bromine, but there's 4 of them, so we'd multiply it by that. And our have number, so the number we'd have, like amount of electrons we do have, is 36 electrons. Now I'll try to get this number to 0, and by doing so I'll subtract it with all the electrons I have. And so looking at the bonds, each one is worth 2 electrons, and there's 4 of them, so that means we'd multiply 2 with 4, and that would give us 8 electrons that we could subtract 36 with. This would come out to about 28 electrons remaining. But I'm not finished yet, because we can use the electrons on the outside of bromine, like they're lone pairs. So we can draw that in for the Lewis dot diagram as we're going to be using them. And now we have these 4 bromides set up, and they all have 6 electrons each. So 6 times 4 would give us 24 electrons that we can sub out into 28. This would give us 4 electrons remaining. The thing is though, is that we have to bring that number down to 0. And there is a way to do that, and we put the remaining 4 into xenon, our central atom. And now, since each lone pair is worth 2 electrons, and we have 2 lone pairs, which is multiplies 2 times 2, which gives us 4 electrons. Now that the Lewis dot diagram is complete, we can figure out the electron group and the geometry of the molecule, which is crucial for later parts of hybridization. We can first determine electron groups, and for this molecule, we can circle the 4 bonds made between xenon and bromine, and the 2 lone pairs, which add up from 4 plus 2, which should be a 6 electron group molecule. And also, we could also figure out the geometry of this information. And if you have a sheet that helps you, you can use it. And as you can see, it should be an octahedral, which is bonding group 6, AX. Now that the problems involving the Lewis dot diagram have been answered, we should look at the condensed electron configuration of the molecule, and this is important. It'll give us important information for the condensed energy diagram, which will translate to hybridization of the molecule. When we do the condensed electron configuration, we should bring out the periodic table as we'll write all about xenon as the central atom. So alright, as you can see here, that's xenon, and it in the p orbital region. Everything before it and up to krypton. We'll also have to take care of three types of orbitals: S, D, and then P. Now we'll finally write down the information. And so we're gonna write xenon in, and then we're gonna put in that, and then we're gonna do like, we're gonna put it like krypton in like square brackets to show that this is condensed. And then we're gonna bring out the periodic table yet again, so we can label it for your understanding. And so it's 1s and all the way down to 5s, to where we can see that, okay, there's 2 electrons within this orbital. And then we move on to D, and always remember that the energy level for D is always going to be 1 less. So if there's going to be 4s, it's going to be 3D. It's going to 5s, it's going to be 4D instead. And we're going to underline all of it because all of it is important for xenon. Okay, and then we're going to write it down for 10, and then we're going to move on to the p orbital region. And it's going to be the exact same as S, except that there's not going to be 1p, there's only going to be 2p, but it's going to be essentially the same thing. So it's going to be 5p, and then you're going to underline everything that would be within like the p orbital region. So we're going to write that down for our condensed electron configuration, and we finally have all the information needed for our condensed energy diagram. To write the diagram, we're going to simply make a graph, and we're going to also have to fill in the information from with like from the left, for the left and for the bottom. And so for the bottom, we're going to have to write in all like the orbitals, so the S, going from S to P and then to D. Also making sure that's correctly spaced. And then for the left, we're just gonna have to write something that signifies potential energy. And so for me, I write it in this way. Now we can, oh yeah, we should also probably space it out so we can keep our work a little bit more organized. And now we can actually write in like the krypton, like with the squared brackets. And we can also write in all the orbitals. So for S, there's only going to be ever 1. For D, there's going to be 5, a little bit above S. And then we do P. And then it's going to have 3 orbitals. And yeah, right. A lot of information. And so now we can actually fill in the orbitals with the electrons. And since this is xenon, these orbitals are all going to be filled up to the max. And so we'll do that now. Now that we have finished the condensed energy diagram, we can now actually move into hybridization. We should now look back onto all the bonds that xenon tetrafluoride also has. And as you can see here, it has 4 sigma bonds and 2 lone pair bonds. And so now that we know that, we're going to write down that information for reference for when we make the graph. We can now make a graph similar to before, except it won't have any of the indicators as before. We'll now put in the orbitals, which were the 6 noted as before, and we'll put in the average distance of all of the orbitals, which is around 4d. For this graph, there will be 6 orbitals, 4 sigma bonds, and 2 lone pairs. Sigma bonds always take priority, and lone pairs come second. Lone pairs are also the only one to come in single bonds. Now we look at lone pair bonds, and since now they're 2, and lone pair bonds will always have 2 electrons within their orbital. There will also be a hybrid orbital name given to this, starting with the hybrid orbital type. And we'll make this pyramid here with all the original orbital types we know of, so S, P, and D. Now we count the number of orbitals there are in the molecule, and so there's 6, so we cross off that amount starting at the top. Now we can find the energy level, and the energy level will always be what S and P are, and for this molecule they're both 5, so we will write 5. And then we can write the hybrid orbital type. So there's 1 S, there would be 3 P's, and there will be 2 D's. And that will finish off our hybridization. Now we can finally make the VSEPR diagram of xenon tetrabromide. Just for memory, there are 6 electrons of group arrangement, which would make this an octahedral. So we are going to draw the octahedral shape similar to what was on that page, with 2 lines coming down, 2 lines coming out of the page, and 2 lines coming into the page, all with their respective shape. Always remember, a wedge means going outside of the page, while dotted lines mean going inside of the page. Also remember to add the central atom, which will be xenon. Now, we need to put the 4 bromines in their respective spots, and the spots that would make the most sense would be these 4 corners. It makes the best shape the molecule can make, which in this case should be something that looks much like a square. And also, just to always remember to place the bonds now. We still have more things to do. We did get the 4 bonds, but we still need to get the last 2 lone pairs. So we will put them in the last 2 remaining spots. With this shape now finished, we can now find out its name and its angle. Starting with the angle, we can see that since this molecule is made into a square-like shape, its angle should be 90 degrees. With 4 electrons trying to equally oppose each other, much like a square, as you can see in the diagram. Now we can figure out the shape. Also taking into consideration the two lone pairs within the molecule. And so we'll take out the sheet. We can see that it's an octahedral and has two lone pairs, which all culminated to being a square planar, being a result of its shape. Now that we've finished hybridization and VSEPR, we could think about additional properties of xenon tetrafluoride. One kind of property that we can learn about this molecule is what kind of bonds exist within the molecule in and of itself. There are three kinds of bonds that we might need to think about for this kind of molecule: polar, covalent, maybe non-polar covalent, or ionic bonds. This would be pretty hard to know without knowing its properties. However, there is one simple solution to this, and it is using electronegativity numbers. First step is to bring out a periodic table with all the electronegativity numbers, and then it would be to find the elements needed, which would be xenon and bromine, in which bromine had an electronegativity number of 2.8, while xenon had an electronegativity number of 2.6. In the end, this would subtract to 0.2. But now, what do we do with this number? Well, there's actually a scale of all of these bonds, which, as you can see here, nonpolar, polar, and ionic bonds. And looking at the electronegativity of xenon tetrafluoride, we can see that electronegativity is extremely low of 0.2, and it is within the range of nonpolar covalence of 0 to 0.5. So therefore, the bonds inside of the atoms should be nonpolar covalent. We'll also compare this molecule to water, more specifically its melting point / boiling point, and seeing whether or not it's higher or lower than water. This is fairly easily lower melting point / boiling point. This is easy to figure out once we figure out the electronegative number of H2O. It will be 3.5 subtract 2.1, and that'll give us an answer of 1.4. Now, 1.4 on the scale is a polar covalent, which is really important because polar covalent is a stronger bond than non-polar covalent. And so that's the ending of this presentation. I hope you give a good percentage. Thank you.